The next thing is we are going to look at the integration of the fuel cell and battery powertrain. So basically, that's the point. We are going to integrate fuel cells and batteries into a holistic system. So basically, we are going to cover how do we optimize the powertrain for the design phase. Let's say we have the short power, and then we have the fuel cell, and we have the fuel cell going to be supplied with hydrogen, and then we may have different hydrogen properties in different regions. And for the batteries, we may use the short-side electricity to charge the batteries. So from a life cycle perspective, now how do we optimize the system? Okay. So basically, we have two parts we have to focus on. Overall, the first part, the research question is how can we design and limit, how do we limit the harmful greenhouse gas emissions from coastal ships using fuel cells and batteries, but still, these system has to be commercially competitive. Okay, so this is a big research question we try to answer, and then we have two approaches to deal with this particular research question. The first one, the figure on the left side, is trying to focus on the design optimization of the hybrid powertrain. Okay, so we frame this, we formulate this problem into a multi-objective optimization problem for design. And basically, we can see we have a lot of constraints coming from the powertrain and also from the vessel. And we have to meet the power requirement and a commercial design, commercial sectors, costs, and also life cycle global warming effects. And also we have the constraints coming from the volume and gravimetric limitations from the vessel. By the end, we are only looking at a small set coming from the overlap of all these constraints and objectives. On the other side, so that's the core bit, basically. Given a hybrid powertrain, how do we use deep reinforced learning to deal with uncertainties imposed by the environment? Because we know that the power requirements coming from the propeller to the powertrain can be quite stochastic, and then even with CFD, it's really difficult to come up with really good observation about the historical power requirements. So basically, the question is, how do we use machine learning to deal with these uncertainties? So basically, we have two parts. The left part is about the agent, and on the right part, we have the environment. So the environment basically is a combination of the propulsion system model and plus the continuous monitoring power requirements. We don't deal with the hydrodynamics, but we take the measurements of the power requirement directly. Basically, these long-term data basically collect over 6 months basically represents the environment. So overall, we have a system model because we are using reinforced learning, which requires a lot of interaction between the system model and reinforced learning agent. So basically, we would need to have a really rapid model to deal with the iteration to collect the experience for the reinforced learning agent. So on the left side, we have a system level layout for the hybrid powertrain. So we are using a DC powertrain architecture. And then basically we have the fuel cells and batteries. And on the other side, we have the shore power to charge the batteries that only when the vessel is at the port. And we have a system level modeling of the propulsion motors and also the service and auxiliary loads. So that's overall system level modeling. And then we also model the fuel cell systems, considering all the auxiliary systems which are supporting the operation of the fuel cells. This is called balancing of the plant. The fuel cell themselves could be at 50% or 55% efficiency, but we really have to consider what are the auxiliary power consumptions coming from the balancing of the plant. On the lower side, we also have the cell level model to represent the electrochemical process happening within the fuel cells. So by the end, the system level modeling looks like this. So basically, we have the hydrogen tank, which is supplying the hydrogen to the fuel cell stacks, and we also have the batteries and the shore power. So basically, on the left side, we would have an energy management system. So this energy management system actually observes what is the current system state. For example, the power level for the fuel cell stacks, and for example, for the batteries, what is the current system state of charge, and what is the power currently being delivered by the battery, and similarly for the fuel cells as well. So by the end, the energy management system will try to coordinate the operation between the fuel cells, batteries, and also the shore power. So on the right side, basically that's more on the electrical modeling of the power electronics, and also the modeling of the motor drives and also motor system. So by the end, we'll have an overall load coming from the loads. So basically, the energy management system also observes the load demands coming from the propulsion motor and also the service loads. So that's the overall system modeling. Basically, we have quite a few different power flows within the system. So electrical power represented in red, and mechanical power, and also hydrogen flow. So into the modeling of the proton exchange memory fuel cell, I'm not going to dive in too much into the circuits, but overall we can see we are having the efficiency coming from the fuel cell. We can see the maximum efficiency points happens around 20% of the load, which is quite different compared to what we normally see 80% for the internal combustion engines, right? But overall, we can have something around, from a system perspective, we can expect 50% efficiency from the fuel cells. And similarly, that's the representation for the battery modeling. So we still have the equivalent circuit modeling for the batteries. So we do the calibration using experiment data, and also we do the validation using experiment data. Basically, you can see there's a really good agreement between the validation set and the battery model prediction. So basically, we try to verify the model works and fits for the purpose. So by the end, first of all, so corresponding to the first part of the methodology, basically we use multi-objective optimization to optimize the sizing for the fuel cells and batteries. Basically, you can see from the external layer is improved multi-object optimization. So basically, so within the external layer, we try to deal with the sizing for the fuel cell and also for the batteries. But more importantly, there's a second layer, because for each sizing combination, let's say for different sizes of fuel cell and battery combinations, we also consider what would be the optimal, how the fuel cell and batteries would be used. In other words, what is the optimal energy management system behind that? We use dynamic programming to do this energy management within the second layer. Basically, by the end, we come up with overall recommendation in terms of the fuel cell and battery sizing solutions. But because it's a multi-objective optimization, on one side, we focus on the cost minimization, but also we'd have to consider what is the overall life cycle emissions coming from the hydrogen, but mostly due to the upstream production and also for the electricity. If we have the vessel operating in different regions or different countries, because we are using different electricity, and then basically the life cycle emissions would be different. So that's the methodology we try to use for the sizing bit. The second part of the methodology is basically how do we use reinforced learning to make decisions. So basically, the problem is at different time steps. So given the fuel cells and batteries, different states, and then given the uncertainty coming from the loads, what is optimal power allocation between the fuel cells, batteries, and the shore power? So basically, we talk about the energy agent and environment interaction framework. So that's a generic framework you have to use if we use reinforced learning to solve the problem. So fundamentally, the reinforced learning agent interacts with the environment by trial and error, but this kind of trial and error is happening in a much smarter way. So by the end, we try to optimize the policy or the energy management strategy by optimizing the experiences we are collecting from these trial and error. So on the right side, basically we can see this is an example of the adaptive network agent we have adopted in this study. So on the upper side, basically we can see that's we have two parts in the environment. So the historical load to the powertrain, and also the hybrid propulsion system model with fuel cells and batteries. On the lower side, basically we can see that's the representation of the deep Q network. So we have the interactions between the agent and the environment. But more importantly, to highlight is by interacting with the environment, So basically, we are collecting the experience. The system transits from state ST to the next system state. At the same time, we're observing a reward signal returned from the environment. So basically, the reward signal represents the cost effectiveness of the action at this certain system state. So by the end, by this kind of interaction, we observe this transition sequence, basically. From system state T, we take the action AT, and then system changes to the next system state. And then we observe a reward signal, which represents the cost effectiveness of the energy management system. And then by the end, we collect a bunch of experience into a memory, and then we use mini batch to update the policy networks. And we have quite a few different techniques to make the training a bit easier. I'm not going to dive too much into the details about value functions and target value functions here, but if you're interested, you can search from the references from the publications we have published in the past. So by the end, one thing to highlight is for the DAP-DeepQ network is only able to deal with discrete action space. So basically means that we can only control the fuel cell power in discrete action space. But on the other side, we have adopted another architecture, which is called actor critic, basically to control the powertrain in continuous action space. And so by the end, once we got the modeling, so basically we did the modeling for this particular case study vessel, and the vessel basically undertakes the voyages between two fixed ports in Denmark. So basically these are two fixed ports, and then we use a historical load profile to represent the environments. Okay. So first of all, in terms of first part, basically we try to optimize the sizing for the fuel cells and batteries. So it's quite important to consider both the cost. The cost basically considers the fuel cost coming from the hydrogen, coming from the electricity, but also the degradation cost coming from the fuel cells and batteries, because every few years we have to replace the fuel cells and batteries due to degradation. And so basically we have two objectives. The first one is global warming emissions coming from the fuels and the electricity. The second objective is about voyage cost, including the cost for the degradation for the power sources and also cost for the energy, electricity and hydrogen. So by the end, we have the trade-off between the two objectives. By the end, you have to select for different scenarios what's the best option for your business case. So if we focused on different countries with different hydrogen produced by different energy sources, basically the solution will be different. From Denmark case with hydrogen via nuclear power, high temperature electrolysis, that be the solution. But on the other side, if there's wind power electrolysis, the solution would be different. So that's for the Denmark case. But if we try to focus on the UK case, so basically we have different solution sets. So I'm not going to dive into the results, but the key message is you have to consider the energy available and characteristics of the power sources and then do the optimization holistically rather than just focus on the vessel. But on the other side, coming back to the optimization of the hybrid powertrain, if we are using fuel cell and batteries, effectively there's no emission coming from the vessels, only water. But what is the life cycle emission? So that's something we have to consider when the vessel is operating in different regions or different countries. And also in terms of results, we are looking at all the autonomous system will be much more expensive than compared to the baseline system, but there's a lot of potential for us to improve. If we can reduce the battery cost and also reduce the fuel cell cost, basically we can see we are going to see the Pareto fronts will be shifting to the right side, to the left side over the improvement of the battery technology and fuel cell technology.